Good morning, Precalculus. Today is April 30th, Thursday, and today we're embarking on a new journey into the world of vectors and parametric equations. So with this, many of you may have been introduced in vectors to vectors when you had me for physics. Those of you that did not have me for physics may have been introduced to them when you had Danny Braddock for physics. Those of you who had not had physics at all at ACLC, I do not know if you have been introduced to vectors. So with vectors, they are an interesting way to deal with things. Rather than sort of talking about sort of a line where you're doing y equals mx, what you have instead is like here, you have your change in x and your change in y, and that's what sort of creates a vector. You're no longer talking about your a relationship between your x and your y for the most part. It's sort of a new form in which we're going to be doing some graphing and some modeling. And it's also one of those things where we've been doing a lot of moments where you're sort of adding things that are going at different angles from each other. And interestingly enough, vectors are one way to greatly simplify that stress of dealing with multiple forces or multiple things going on at once, like say a airplane flying in a certain direction and there's like a wind blowing and you're trying to figure out how fast this plane is going. There's a lot of math that you could do to sort of solve that. And one of the easiest ways is through using vectors. So to start us off, we're going to go through this vector line dance. I encourage you that if you're sort of like want to test it out, to take this time to sort of pause and attempt these vector line dances on your own. For the sketches, what I would suggest doing is sort of in your notebook, sort of choosing a starting point and sort of doing that and sort of creating a different one for each of these numbers. If you want to, you could also like physically stand up and do the moves. So then you're in a vector line dance. It's up to you really what you want to do. If you want to call that your physical activity of the day, woo! Otherwise, we're going to sort of keep doing some math. So now would be the perfect time to pause if you want to work through it. And I'm going through now. All right. So with this, we have a few different things. So this first one right here, step one, you move right to, and as I said, sort of change in x, change in y. And then we use our angle like we do for the unit circle. So remember, unit circle going to just to the right is an angle of 0. Magnitude is how far you actually went, so that would be like the radius of this new circle. So in this case, since we moved right to, our radius is 2 units, so our magnitude is 2 units. Now if we do up 1, if we draw it, fingers crossed, I don't mess it up. So we go up 1, so I'll choose right here, and we'll go up 1. We do that, and bam. So in terms of angle and magnitude, if we think about it, what I'll say is our angle, since it's straight up and down, based on a unit circle, that would be 90 degrees. And since we went up 1 unit, that would be a magnitude of 1. Now, we're going to go back 2, so that would be down 2. So if we go back 2, although to be perfectly honest, I don't know why they called it back 2 when it really should be down 2. So you're going to go back to, so if we think about it, the angle we have here, there's a couple different choices. We could say negative 90 if we wanted to go backwards on it, or we could say 270 degrees, and then our magnitude of this, because we went back 2 units, our magnitude is 2 units. Now, in number 4, we go up 1, left 1. So if we think about it, we went in the negative x direction 1 unit and the positive y direction 1 unit. And then the magnitude would be sort of the distance we displace. So our displacement in this case would be root 2 because we have a little triangle, 1, 1, and then this would be root 2. So now we're going to do left 2. So if we think about it, if we want to think of the vector we have, left would be in the negative x direction. And so when we do our vector with our angle brackets, we would have negative 2. And then in our y direction, we didn't move any in the y direction. So that would be a 0. Now when we think about it, angle, let's draw it, and then we'll think about the angle and magnitude. So drawing it, bam, bam. And then our angle, if we think about it, it's now in the negative x direction, which that was 180 on our unit circle. And our magnitude is our displacement, which in this case is 2. The displacement's always going to be positive. You're not going to really do a negative displacement because it's always possible to write a negative displacement as a positive displacement in the opposite direction. Now we're going to go up 1, right 1. So we go up 1, right 1. So we go bam, bam, and we draw it. And so we get 1, 1. Now if we think of the angle, it's a 45, 45, 90 right triangle. So we would have 45. And then the length of the hypotenuse is our magnitude, which in this case would be same as this one, which is root 2. Now we're going to go down 1, right 1. So if we go down, right, put it here, here, and then wha-bam. And so when we do that, down 1, right 1. So first thing we do is the right, because our left coordinate is always our x coordinate, or x change in x. So that one was a positive 1. And then our down 1 was a negative 1, because that was the negative y direction. And then in terms of our angles, we could say it's negative 45, or we can go all the way around the circle and say it was 315 degrees, comma, once again, 45, 45, 90 triangle with 1 and 1, so that would be root 2. So that's what we have here for number 1. Now, with this, we usually do the positive angles. So for any vector you draw, it's probably going to be something between 0 and 360 degrees in terms of your angle. With this, and so those are called the standard angles, as it sort of says here in the book. We have our standard angles, which are the angles sort of the same way we measure on the unit circle from above the x-axis. And then we have our magnitude, which is sort of the length of our vector right here, which is basically, if we have it in sort of a diagonal, it would be the hypotenuse of our displacement. So that would be the magnitude, sort of thinking of triangles again. And so with this, there's a few things we can do. If we think about it, if you were to actually do this, your sketches might actually be different than mine. You might have put yours in a different place, because one of the things that vectors don't care about is position. They only care about displacement. And so with, say, this one right here, you could have drawn it over here. And in both cases, they are the same vector. They're just in different positions. And so one of the key things is that the location doesn't matter for a vector. It's mostly about displacement. So it doesn't matter what position you're at. It just matters how much changed. So with, like, if we look at 10-2, one of the things that happens is you have two vectors that are the same magnitude and direction. They are basically equivalent vectors. And so they represent the same instructions. They're telling you go 4 steps to the right, and that would be what you would do regardless. And they have the same length, and they are equivalent vectors. So one of the things I would definitely encourage you all to do is to take this information about vectors, sort of based on what I showed you with 10-1 and what's in here in the vector notes, in the math notes about vector notation. Usually if we have a vector between 2 points, we do something like, if it's between points A and B, so if we have point A and we have point B, we could say the vector, it's going to be sort of remind you of ray notation from geometry. So we'd have vector AB. Alternatively, we could call it a particular letter. Usually we have 3 primary letters. We have U, we have V, and we have W. These are the common vector labels we use. Mostly for mathematics, they're the U, V, and W vectors. There's also J, K, and L. Which are also commonly used when it comes to vectors. Those are more so used when we're looking at matrices, especially in 3-dimensional space. So for the most part, though, we'll probably end up using V and W, or U and V, or J and K, is what you would expect to see during this time that we're working with vectors. And overall, they're pretty cool. So in 10-3, one of the things you're going to be doing is we have all of these different vector images here. And so what you're going to do is you're going to name pairs of equivalent vectors. So looking through all of these, you're going to pair them off and be like, okay, these two are the same, these two are equivalent, these two are equivalent. And so what we're going to do, so you're going to be doing that, and then one of the things you're going to see is there's a way to add the vectors geometrically. So one of the things you can do is, say in this vector P, if you wanted to add P and M, or R and M, what you would do is you would do a tail to tip. So basically what would happen is you would take this vector M, which is a -3, a 0, -3 vector, and you would put it at the end of this R vector. So what it would look like, one second, bam. So with this, you have your vectors, and so if we add them, one of the ways we can add them is geometrically. So if we wanted to add R and M, what we could do is we can just take this M vector, which I believe I can just use the lasso tool. And what I can do is I can then move it down below. We can go tail to tip. It was close. And then our new vector would be basically, we start from where the R vector is and we go to where the M vector ends. So if we add them together, we end up with a vector. Oops, if I can draw, let me make this a little bit bigger. We go from here to here, and then we draw it. And if we wanted to say the length of this vector, well, we go down 1. If we were to create this vector, so this would be R plus M. But if we were to write this vector, well, we go down 1, so that would be a -1 over here. And then we went over 1, 2, 3, 4, 5, 6, 7. So we'd have a vector of 7, -1. And that would be what our R plus M vector would be. Now, one of the things you can do is, using a little bit of trig, you can convert, using Pythagorean's theorem, you can convert this to a magnitude by basically, think of these two as the legs of your triangle. You square them and you get that. As well as, one of the things you can do is find the angle you're using, which would involve basically using tangent on these two numbers, because if you think about it, this would be your adjacent angle, your adjacent side, and this would be your opposite side. And then you could convert that into a standard angle because it's going to give you a negative value for your tangent function. It's going to give you a negative angle, so you'd have to add 360 to it to get your standard angle in order to have it function properly. But these are sort of the ideas of how you add your vectors. One of the things you can do is do it algebraically, where you would write out both of your vectors in component form right here. And then you would just add your x coordinates, you'd add your y coordinates, and that would give you a resultant vector, which is something we're going to investigate a bit more tomorrow, I think, or it might be Monday. But right now we're just focusing on these vectors geometrically, but if you want to skip ahead and sort of see how it's done algebraically, I encourage you to do so. So this is going to end the video for today in terms of the rest of what you need to complete for this. So we've started a little bit into 10-4. I encourage you to sort of finish it, and then 10-6 right here would be a sort of a good thing to complete. And that one has the answers in the back of the book, which you can do, which I encourage you all to do. So in 10-6, they talk about bearings, which is something that's commonly used by both planes and boats. And also if you've ever done orienteering, usually you talk about bearings. So angles off of north rather than angles off of, say, the x-axis, which makes a little bit of a difference. So what I'd suggest doing is you sort of go through that just to be familiar with bearings. We're not going to go too deep into it, but it is just kind of nice to know in case you ever have an emergency where you need to be somewhere or you get lost and have phone communication but no GPS. Really rare communicate, like maybe it'll save your life one day. Probably not, but we'll see. So that ends it for today. If you have any questions, message me on Discord, Jupiter, Hangouts, wherever really. Just contact me. I'm thinking I will start having some live sessions, and I'll send you some emails about that later on, and have a good day.